We'll look at probability and some of the basics surrounding probabilities we start to look at as we start to move forward in the course. So with this, we're going to be able to use some of the terminology of probability and then calculate probabilities using things like the multiplication, addition, and complement rules or properties. So to get this thing kind of going, I want to remind you guys of a function in your calculator, which is you can simulate some of these random events that we're about to start talking about. So using a random number generator, we can flip an imaginary coin. So let's say we're going to flip this coin, so we have heads or tails. So we have two options. Now we're going to assign some random numbers to the events. So what we could do, we could randomly pick between 0 and 9. Maybe the first 5 are heads, the second 5 are tails, or evens or heads, odds or tails. Probably more of where I would go. Just use 1 and 2. 1 being heads, tails being 2. All right, decide on how many trials you want to do, and then execute the simulation. So what we could end up doing here, if we're going to go through this process, we'd end up using that random integer function, and then 1 comma 2, and then a lot of folks, a lot of classes were doing like 5 trials at a time. So that would flip a coin 5 times in a row, 1 being heads, 2 being tails. So let's say that you did this, and you ended up with 1 1 2 1 2. Well, that's heads, heads, tails, tails. The probability of heads there would be 2 out of 5, and 3 out of 5. Tails would be 2 out of 5. Let's say we did it 2 more times. And if you give me a second, I'll type this in my calculator. And I got 2 2 2 1 2. So that's tails, 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 heads, tails. And then 1 2 2 1 1, which is heads, tails, heads, heads. So here we got a 1 out of 5 for heads, 4 out of 5 for tails, 2 out of 5, and 3 out of 5 again. So if we start to combine these results, what we should start to see is out of these 15 trials, we should, as we increase our sample size, we do more and more, we should be getting really close to a 50-50 shot, which you can see is here. Now, 2 of my trials actually were pretty close, the first and third trial. But what we're starting to see is, in this short run, we have this chance behavior, and it seems kind of random, especially trial 2 right here. Got a lot of tails and not many heads. So these are all empirical or experimental probabilities. This is something we've done. We've observed a phenomenon. So that's empirical probability. So the way probability works is that the long run relative frequency, as n increases, number of trials, what we're going to see is that the relative frequency, or really that's just saying the probability, or the proportion. We've dealt with that before when we were doing histograms and ogives. So this probability of some event will settle down to a true probability as n is increasing, right? As the number of trials goes up and up. You could do a big simulation if you wanted to start to see how this thing works. And this is how you could do it. Use a list and then highlight L1. So go up there, and then when L1 is highlighted, do your random integer function. You can flip the coin 200 times. And the reason I'm putting it on the list is because I could easily create a histogram. And then this kind of walks you through, you could set up your window properly. And really we just go from 1 to 3 because, well, we've just got a big list of 1s and 2s. And the X scale, by separating at 1s, what it will do is heads will be the first bin, tails will be the second. And then, think about the Y min and Y max. Well, how many of each would you expect on 200 trials? So maybe you take your Y max up to about 75 to make sure that you have enough room. And then you're not going to have any below, so you can do 0 there. And then hit the trace button, and you can see how many heads, how many tails. Now, as you're starting to get into this, what you see is if we keep doing this thing over and over again, what we're getting closer to is what's called a theoretical probability. So the theoretical probability of flipping a coin is 1/2. So if we kept flipping and flipping and flipping, we should get, according to the law of large numbers, which we've already touched on, as the number of trials increases, the empirical probability, what we actually do, right? Empiricals, you did it, should get very, very close to the theoretical probability. So there's another look at the law of large numbers using a little bit more of our terminology in terms of the two different types of probability. Empirical, what you're physically doing should get close to theoretical, the true value. Right? So theoretical is the quote-unquote true value. All right. So some of the terminology. We have trial, which is an event, outcome. You're usually told, hey, what's the probability of this, or what's the probability of that happening? That's an outcome. And then sample space is the set of all possible outcomes. So sometimes it makes sense to actually write out the whole sample space. Here's a quick example. We're going to flip a coin 3 times. And the outcome we're after is that 2 of the 3 will have 2 of the 3 coins will have tails. So really we're looking for what's the probability we get 2 tails. Now this is an example where actually writing out the whole sample space would help us out. So here's the whole sample space. You'd have 3 heads, 2 heads and a tails and 2 heads. You guys can read those. And the ones that we're after are 2 tails. So there's 2 tails, there's 2 tails, there's 2 tails. So that would be 3 out of a total 8. Another application of the sample space. List the sample space and let's see if these events are equally likely. So we're going to roll 2 dice and record the sum showing. So we could get 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And first reaction to that is, oh yeah, like it seems like they should be equally likely. But if we were to write out the sample space, so how is it that you roll a 2? Well, you roll a 2 by rolling a 1 and a 1. How do you roll a 3? Well, you could roll a 1 and a 2 or a 2 and a 1. Right? And so on and so forth. So there's 3 ways to roll a 4. 1, 3, a 3, a 1, a 2, and a 2. So on and so forth. So you keep going. So 7, you could roll a 1 and a 6, a 6 and a 1, a 2 and a 5, a 5 and a 2, a 3 then a 4, or a 4 then a 3. So right away we're starting to see there's more ways to roll a 7 than a 2. When we get to 8, we're going to start coming back down, right? We can't roll a 1 and a 7. And down we go until we get to 12, which is there's only one way to roll a 12, which is a 6 and a 6. So the total number of outcomes here, there's 36 total outcomes if we were to go through and count all these up. So there's 36 different outcomes. So in terms of probability, just how many ways to roll each die? There's 6 ways to roll a 7. So the probability of a 7 is 6 out of 36, which tells us these events are not equally as likely. There's a good application of a sample space. Just write it out to see. How about this one? The number of male children in a family planning on having 3 kids. So they can either have 0 kids, 0 boys. They could have 1 boy. They could have 2 boys. Or they could have 3 boys. Right? But to have 0 boys, that means that they have all girls. If they have 1 boy, think about it. They could have the oldest could be a boy, the middle could be a boy, or the last. So there's actually 3 ways to have 1 boy. 2 boys, they could have 2 boys and a girl. They could have a boy first and last, or they could have a boy second and third. So there's 3 ways to have 2 boys. And then in terms of having 3 boys, 1 way. So in terms of probabilities, the total sample space here is 8. They have 8 different possibilities. So there's 1 way to have 0 boys. 3 ways to have 1, 3 ways to have 2, 1 way to have 3. So here, they are more likely to have either 1 or 2 boys than all boys or no boys. As you start thinking through some of this stuff, some of the things we need to keep in mind. So probabilities are always between 0 and 1. Probability always between 0 and 1. You can never have a negative probability. You can never have a probability of over 100%. So really, there's a 0 to 100% chance of anything happening. Sample space, when you add up all the sample spaces, it should add up to be 1. Right? Look at this. Add those up. 1/8 plus 3/8 plus 3/8 plus 1/8. Add those up and it's equal to 1. If you go to the previous page, add all these up. 1 plus 2 plus 3, etc., etc. That adds up to be 1. So this is what's called the complement. Sometimes you see it as a little C written above, complement. Or sometimes I'll put a bar over the top. That means the same thing. It's just whatever text you're talking about. So the probability of something occurring is 1 minus the probability it does not occur. So here's the thing. You think about this. The probability of A occurring plus the probability that A doesn't occur. So think about this. The probability that it rains or it doesn't rain. That's always going to be 1. And what that formula has done is it's just rewritten this. It's subtracted probability of A complement to the other side. So the probability of an event occurring is 1 minus the probability it does not occur. And there's a really cool use of that here in just a little bit. If you have the U union, probability of A or B, you would add A and B. And this is if the events are disjoint, which again we'll talk about as the course progresses. And then the intersection, or A and B, would be multiplying. And that's if the events are independent. These are 2 pretty big keys right here. And as the unit progresses, we'll talk more and more about those. So here we go. In a standard bag of yellow and red and a standard bag of M&Ms make up 20% each of the candies, orange, blue, and green 10%, the rest are brown. What's the probability we get a brown? Well, if yellow is 20%, red is 20%, orange is 10, blue is 10, green is 10, add those up, 20, 40, 60, 70. That means that 30% of those are brown, just because the whole probability, right? 1 minus 0.7 is 0.30. Yellow or orange. So the word or pretty much always tells you to add. If you see the word or, it's saying add. If you see the word and, it means multiply. Or means to add. So, excuse me. Yellow plus orange, 30%. Not green. So if 10% of them are green, 1 minus 10% is 90. And then striped, there are no stripes, so there's 0. If you pick 3 in a row and then replace, so all brown. So in other words, the probability of brown and brown and brown and means multiply. So there's a probability of brown, so we just multiply 0.3 times 0.3 times 0.3. The third one is the only red, so that'd be probability of not red and not red. I'll use the bar over the top, and then red. All right, so that'd be not red, so 20% of red, so that'd be 0.8 times 0.8. When we finally get our red, 0.8 times 0.8 times 0.2 is your probability of 0.128. So maybe here's an example where they decided to add a color to the standard lineup, and the winner was purple. So in the U.S., 42% of those who voted said purple, 37% teal, 19% said pink. So the sample space would be purple, teal, or pink. Those were the ones that people picked from. So verify these first 2 properties are true. Well, the probability of each of these events is, in fact, between 0 and 1, right? 0.42, 0.37, 0.19. But does the whole sample space add up to be 1? So 0.42 plus 0.37, 0.19. That actually does not equal 1, which tells us that there's some other event for no preference. Right? These 3 things actually add up to be 0.98, which means 2% of people said none. So if we did something else, and instead of in the U.S., we talk about in Japan, 38% said pink, 36% teal, and 16% purple. All right, what's the probability of pink or teal? So just add, or means add, right? If we pick 2 respondents at random, what's the probability they both said purple? So that'd be purple and purple, which means you're going to multiply. So 0.6 times 0.6. If we pick 3 at random, what's the probability at least one said purple? Okay, so this one's a little bit tricky. At least one purple means that there could have been 1 purple and 2 not purple, or 2 purple and 1 not purple, or all 3 said purple, right? At least 1 purple means 1, 2, or 3. This gets a little complicated because there's 3 ways that someone could have said at least 1 purple. It could have been purple and not and not. It could have been not, and then the second person said purple and the third person said no. Or it could have been the first 2 didn't want purple and the third one did. So there's 3 different ways that you can combine 1 purple with 2 non-purples, and that's what this 3 right there is. Same thing here. We could have had purple, purple, not purple, purple, not purple, purple, or not, and then the 2 that did. So there are 3 ways to come up with 2. And then there's only one way that all 3 people could say purple, so there's where the 0.16 comes in. And so if you were to do this, all right, put all that stuff together. I don't know if you can quite read that, but that's 0.407. Now that's kind of the long way of doing this. There is actually an easier way. And it's this idea here, probability of at least one purple is the same thing as 1 minus a probability of no purple. This is a phenomenal use of the complement rule. I think I was spelling that wrong. I apologize. The complement rule says the probability of at least one, whatever it is, the opposite of at least one, if I told you that I had at least $1 in my pocket, the opposite of that, the one thing you would know that I don't have in my pocket is no money. Right? Think about that. If I have at least $1, well, you don't know how much money I do have, but you know for certain I don't have no money, if that makes sense. So this is a huge rule that's very, very helpful moving forward, and that's called the complement rule. So whenever you see the term at least one, what should be going off in your head is a little alarm saying, okay, at least one. The really easy way to do that is 1 minus none. So if we look up here with no purple, well, 16% were purple, which means no purple, no purple, no purple. There's only one way to get no purples the whole time, and that's none, none, none. So we just do 1 minus not purple, not purple, not purple, which would be the same exact thing. Notice 0.407 again. We saw right there.